All right, as we begin now graphing and shifting our functions, before we start with the function, I want to go back to what we did in chapter 1 with a circle, because you already have half of what you need mastered. When we did circles, if you recall, the center of a circle was always located with the shift that occurred with x and y. If you remember, this always referred to the horizontal component, and the y value always referred to the vertical component that made up the center. So when we did this before, remember our center was always whatever went with the x value and whatever went with the y value. So mathematics builds on itself. Don't change what you already know to be true. We already know how to shift left and right. We already know how to shift up and down. So we're halfway done, you guys. So if I introduce the idea of a function to you, and let's look at our library of functions. For example, the square function. And let's say we just talk about the square function as y equals x minus h squared. Well, if you'll notice, you know what? Let's go ahead and I want to throw a number at the end as well. That could be a positive or a negative number. And I want to show you that you don't need to make it more complicated if we remember what we've already done. Notice what I'm going to do. I'm going to first, you don't have to do this, but I'm going to first move the k to the other side so that it looks very familiar to what we have done with an h and a k in the past. And if I choose to, again, you don't have to group them, but look at what we actually have. We know what we did with the circle. Well, we're going to apply that exact same concept to a parabola. This would mean that the graph is going to shift, so horizontal shift, because it's grouped with x, which goes in the horizontal direction. This value, which I moved over to be with the y value, implies that it's going to shift vertically. Okay, so I'm not going to worry about what you might call that point, but the idea is the entire graph has shifted. So I'm going to do it again, because we know what the parabola looks like. We went over that library last section. So let's say I give you an absolute value function. Y equal, you know what, I'm actually going to give you an example. Let's say I give you a parabola, x minus 3 squared plus 4. This is a square function, it's a parabola. But instead of memorizing, let's analyze. If you choose to, you could bring this value to the left side and make that a y minus 4. And what's happened is, in our horizontal direction with the x, this entire parabola, and you learned the parent graph the other day, this entire parabola moved horizontal positive 3. This entire parabola moved in the y direction, vertical, positive 4. So we've actually now learned that this vertex is now right 3, up 4. Once you've taken care of the vertex, when we go to graph in a moment, all we've done is shifted the regular parabola right 3, up 4. Let's say I give you absolute value. Absolute value, we know that this is the absolute value graph. you have your library of functions. You have all the graphs that we discussed in section 2.4. Okay? So all this is telling me is, and if you choose to, you can move this to the other side. Now you have grouped all your x's together naturally because the grouping symbol absolute value. And we've grouped the other constant to the other side, so it's going to tell what's going to happen in the y direction. And eventually, a lot of you may already see that's going to simply move it up. But for now, whatever's in the x-axis is the horizontal shift. So it's going to shift horizontally, +3 to the right. And this is going to be the vertical shift because it's with the y values. I forgot a syllable, forgot a letter. And so we would end up with our starting point or our vertex, right 4, up 3. And you know what, I think what I'd rather say is start from. I'm going to kind of look at this as a starting point. Okay? The reason I just changed my mind is, let's give you the square root graph. Y equals the square root of x minus 3 plus 4. You don't have to keep memorizing things over and over. If I move the 4 to the other side, we already know what the square root graph looks like. And now, because this is grouped with the x inside the square root, this is our horizontal shift. Because the 4 is grouped with the y value, that's our vertical shift. Which means this square root graph, and again, you already have what the parent function looks like. You already have the shape. As soon as we know what the shape is, we now know that it is going to start at the point 3 in the horizontal direction, 4 in the vertical direction. And we could do this for all those graphs. Let's say I give you the cubed graph. And let's say I give you x minus 3 cubed plus 4. Well, again, you can leave this 4 here and it'll tell you it automatically is +4 and it's going to go up. Or you can move it to the other side to put it with the y values. And hopefully you're starting to see a pattern. That means it's going to go vertically 4, horizontally 3. So that means that this cube graph, we already know the shape of the cube graph, is going to start, instead of at the origin at 0, 0, the starting point has shifted right 3, up 4. So you guys, you already know half of how to graph. So let's look at that before we look at the only other piece of information. Because you've already figured out how to shift left and right. Now let's practice. So keep your library of functions nearby, or open your book and look at section 2.4 where all the graphs of the parent graphs are there. And let's practice this skill first. Okay, let's practice this first. So let's say we start with the following. sketch the graph. Might as well do the one we've been practicing. Let's go x minus 3 squared plus 4. So when we look at our library function, that's the square function. That's a square function. So this is a parabola. And we know that the parent graph starts at 0, 0. We know the parent graph is the graph y equals x squared. And we already have this. If x is 0, x squared is 0. If x is 1, x squared is 1. If x is 2, x squared is 4. Negative 1, x squared is 1. Negative 2, our y value would be 4. So what I'm going to start with is the parent graph. I'm going to start with the original. When you work these out, when you do your homework, you test your quiz, you need to make sure you either use graph paper, or if you don't have graph paper available, make sure you label the axes and give several points so that we have points of reference. I'm just going like 5 or 6 in each direction. And I'm going to start with the parent graph. The parent graph, all these graphs we talked about the other day, they all hover around or touch the origin depending on what the graph is. So if I look at this parabola, I'm going to start at 0, 0. If I go to the right with x, right 1, up 1. Right 2, up 4. Right 3, up 9. If I go to the left 1, I go up 1. Left 2, I go up 4. Left 3, I go up 9. And if I graph this parent graph, which is what we did the other day, we get a parabola that looks pretty much symmetric. It's even because it reflects across the y-axis. And there's our parent graph. Any kind of equation that is an x squared graph will resemble this one. If it's an x squared, it's going to resemble a parabola. Now, based on what we just did, we now know where to begin from. We now know that this graph is going to shift horizontally three and vertically 4. So that means this graph is going to start at the point 3, 4. So if I start at the point 3, 4, right 3, up 4, here's the point 3, 4. It's as if you have taken your origin, it's as if you have taken your vertex, and you have taken this point at 0, 0 and shifted right 3, up 4. So all you literally would have to do is copy and paste. So from this point 3, 4, so think about this point now as 3, 4. If I go to the right 1, I'm over at 4, I only go up 1. If I go to the right 2, 1, 2, I go up 4. So if I go to the right 2, up 4. If I go to the right 2, and I go up, if I go to the right 2, up 4 from here, right 2, up 4. Okay. Another way to look at it, you'll notice what I wrote over here in blue, because that's my shift. I already said I go right 3, up 4. So if I take every single one of these numbers and I add 3 to it, 1 plus 3 is the number 4. 2 plus 3 is the number 5. Negative 1 plus 3 is 2. Negative 2 plus 3 is 1. If I add 4 to all the y values, because we're going up, the original point started at 4, but we finish at 8. This point finishes at 5. This point finishes at 5. This point finishes at 8. And all you have to do is graph the outside points. 1, 8. 2, 3, 4, 5, 6, 7, 8. 1, 8. 2, 5. 3, 4. 4, 5. 5, 8. And when we finish, it should look as if we have copied and pasted our graph, right 3, up 4. Okay, so we're going to take a look at an absolute value graph with a similar shift. All right, so let's take a look at an absolute value graph. Because you get the idea, all you need is the parent graph. So if I give you y equals the absolute value of x plus 2 minus 3. Well, we already know what the parent graph is. We already know this is the absolute value graph. So if I identify the parent graph, the parent function, this would be y equals the absolute value of x. So we already know what that one looks like. So I'm going to sketch a table of values, but you already have that. Again, if I start at the origin, absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. Negative 1, absolute value is 1. Absolute value negative 2 is 2. So that's our parent graph. You'll notice again, it starts at 0, 0 or hovers near 0, 0. Here's x, here's y. 1, 2, 3, 4, 5. And if I start with what I know, and I start with the parent graph, 0, 0. If I go to the right 1, I go up 1. If I go to the right 2, I go up 2. If I go to the left of 0, 1, I go up 1. And I go to negative 2, 2. So here's your parent graph. When you're doing homework, oftentimes it's nice to just make this a dotted pencil line, something like that. I'll do that on the next one. Now all I'm simply going to do is pick that graph up and shift it. It shifts horizontally, negative 2. And if I bring this to the other side, or you may notice if I bring it to the other side, that's a plus 3. It shifts vertically down 3. So what does that mean? That means our vertex, our origin shifts in the horizontal direction to the left 2, down 3. Left 2, down 3. You can also think of it this way. It went left, that's horizontal. It went down, that's vertical. So if I subtract 2, I shift everything to the left 2. Negative 2 minus 2 is negative 4. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2. 1 minus 2, 2 minus 2. At the same time it's shifted left 2, we need to move down 3. So subtract 3. Subtract 3. Subtract 3. Subtract 3. subtract 3. And simply graph those points. I'm going to have the point -4, -1. I'm going to have the point -3, -2. -2, -3. So there's our vertex. -1, -2, 0, -1. And there's our new function. One more time. I'll do the square root function. Y equals the square root of x minus 4 plus 1. You can leave it that way. You can move the 1 to the other side if that helps you. So I'll do that on this one if that helps. But before we worry about shifting it, let's take a look at our parent function. Our parent function means, think about what this equation would look like if you eliminated adding, subtracting, multiplying, or dividing. So if I eliminate all adding and subtracting, you'll notice that we have the square root of x. If I eliminate all adding and subtracting, you'll notice we have y equals the square root of x. So that means our parent graph is y equals the square root of x. So if I start that graph, and again, you can always create a table of values. It's always nice to start with 0. Square root of 0 is 0. Square root of 1 is 1. The square root of 2 is a decimal. The square root of 3 is a decimal. The square root of 4 is 2. So I'm going to choose 4 so I get an output of a nice whole number. Square root of 5 is a decimal. I'm not going to pick it. Square root of 6, decimal. Square root of 7, decimal. But the square root of 9 is 3. So I'm going to choose nice integers for my answer. Now, again, this point is on the graph. Square root of a negative? Well, we know the square root of a negative is imaginary. So that is not real, so it is not on the graph. So if I take a few minutes and I graph my parent graph, I simply graph these points that we have chosen for the parent function. When x is 0, y is 0. When x is 1, the square root of 1 is 1. I have to go all the way to the number 4 before I can go up to the number 2. I apologize. I'd have to go all the way to the number 9. Maybe this will fit. 1, 2, 3, 4, 5, 6, 7, 8, 9. Before I can go up to the number 3. So the square root graph is half of a parabola. All right, now I'm going to do this transformation that we just talked about. This says in the x direction, I'm going to shift right 4, and I'm going to shift up 1. Therefore, in the horizontal direction, I am going to add 4. And in the y direction, I am going to add 1 because I'm going up. Well, if it's imaginary, we'd ignore it. 0 plus 4, 1 plus 4, 4 plus 4, 9 plus 4. Add 1, 0 plus 1. And now we have our shifted points. This origin is going to shift from 0, 0. It's going to go right 4, up 1. And from there, I'm graphing the exact same points. So 5, 2, 8, 3. Sorry about that. A little bit off. and my graph shifted right 4, up 1. So guys, no matter what the shape I give you, that's how we shift left, right, up, down. So we've taken care of all adding and subtracting. The only thing left to do is multiplying. And dividing is the same as multiplying by a reciprocal. So I'm going to take the same basic shapes, maybe I'll choose one of the others, and we will take a look at what happens when we multiply. These are called compressions and stretches. Okay? So if I give you something like this, let's take a look at a compression, meaning getting compressed, or a stretch where it widens out. You might think of it as a stretch. Compression or stretch. For any function, given any function, any of them from that list, linear function, constant function, square root, square function, cubed root, cube function, absolute value, greatest integer, reciprocal function, all the ones we did the other day. If we take and multiply that function by a number on the outside, that is a vertical stretch. You did that with lines. This would be as if you have the equation of a line. Whatever was out front was a slope. So this is a vertical stretch. Well, it's a stretch, meaning it's getting steeper if a is greater than 1. It's a stretch, which means it's getting steeper. Narrower. Now you can think of it that way, narrow or steep. Okay. It's a compression if a is less than 1, but still positive. So it still has to be positive, but it's a fraction, so it's less than 1. So you can think of this as being wider. If I vertically compress something, the sides go wider. But if I instead choose to keep the function as it is, but multiply the x value, I don't know if you've seen this before. I don't think so. This means that it's going to be a stretch or a compression horizontally. It's a horizontal stretch, this time if it's a fraction. And it's a vertical stretch okay. Whoops, I just wrote the same thing. Horizontal stretch. Sorry about that. My mistake there. It's a horizontal stretch whenever it's a vertical compression. So if I compress vertically, it stretches horizontally. Similarly, if it stretches horizontally, it shrinks vertically. And then the last two, and then we'll practice one or two, is what happens if we have negated the function, if we have a negative out front. If we have a negative out front, the y values have been negated because it says the opposite of f of x. So if the y values have been negated, it reflects over the x-axis. Whereas if I put the negative sign inside the function itself, and I'll show you with an example, If I put it inside the function itself, then that means it's a reflection in the x direction. All the x's are negated, which means it's a reflection over the y-axis. Okay. So let's take a look at a couple of examples of this. All right, so let's take a look at a couple of examples. Let's try one like y equals 3x squared plus 2. Well, what we do is we identify, remember, take away, cover up any adding, subtracting, multiplying, or dividing. So if I cover up any adding, subtracting, multiplying, or dividing, oh, that's a graph, I don't want to put that out there. If I cover that up and I cover that up, notice all we have is x squared. So we know that the parent function is whatever we get when we cover up adding, subtracting, multiplying, or dividing. Now, we also know from what we just did that there's nothing inside here grouped with the x. So if you prefer, you can move the 2 to the left side, and you could notice that there's nothing that's being squared with the x. So this follows the same format that says in the horizontal direction, there's no movement. Okay? Horizontal shift, nothing. Vertical shift, 2. So that tells us where our starting point is. Okay? So again, I'm going to start with the parent graph, but this time I'm going to just make a dotted graph. So if you're using your pencil or pen, it's a nice frame of reference. So in this case, we already know what the parent graph looks like. I'm going to make a little table of values. Some of you may prefer having a table of values. Others may not need it. The parent graph, which is the one that's in black right here, if x is 0, 0 squared is 0. If x is negative 2, y is 4. If x is negative 1, negative 1 squared is 1. If x is positive 1, positive 2. And that gives us a shape. We already know it's a basic parabola. Right 1, up 1. Right 2, up 4. Left 1, up 1. Left 2, up 4. And we know it's a parabola, so I'm going to do this. There's my parent graph. Now from there, I want to shift vertically 2. But I also need to keep in mind that I have a 3 out front, which means, excuse me, I have multiplied my function outside of the x, I've multiplied it by a number. So that 3 is going to indicate that we have a vertical stretch, which means if it's vertical, the y values are 3 times higher than they normally would have been. So, order of operations, I'm going to take all my x values and multiply them by 3. Negative 2 times 3, negative 1 times 3, 0 times 3. Okay. And all our y values, we went vertically up 2. And so you'll now notice that our original starting point was 0, 0. But we knew that it was supposed to go in the x direction nothing and in the y direction positive 2. So notice it's now located in the x direction 0 and the y direction positive 2. But now our y values and our x values are dependent upon what's happened. So our x values, say, take them and multiply them by 3 times what they were before. And our y values, we need to make sure we add 2. Okay, I had noticed that I had glanced at a horizontal instead of a vertical. We even wrote vertical stretch. So notice I've erased this to start over. The vertical stretch is 3 times what it was before. The vertical stretch is the y value because the y values are vertical. So because the vertical stretch, okay, the vertical stretch of 3 means each of our y values is 3 times higher. Okay, it's going to be 3 times whatever it was before plus 2. So I'm going to take 3 times 4 is 12, add 2. 1 times 3 is 3, but I have to add 2. All right, so if we keep following this pattern and we say, okay, well, remember 3 times 4 is 12, and then our vertical addition of 2. 3 times 1 is 3 plus 2. 3 times 0 is 0 plus 2. 3 times 1 is 3 plus 2. 3 times 4 is 12 plus 2. So our new y value will be 14. 5, 2, 5, and 14. Remember, we had no shift in the x direction, so our x values stay the same. So now if I graph negative 2, 14, apparently I'm going to go off my graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I apologize. But after having a geometry class, we know you just work right on through whatever paper's there. Negative 1, we're at 5. 1, 2, 3, 4, 5. 0, we're at 2. 1, we're at 5. And 2, we're up here at 14. So when I finish, it should look as if my graph is narrower and shifted up 3. Okay. And the last one I want to do is I want to do not so much a reflection up or down as much as left and right. So I'm going to give you this graph. The square root of the opposite of x plus 2 minus 3. So we know the parent graph. The parent function is what you get when you remove or cover up adding, subtracting, and multiplying. So if I cover up adding and subtracting and multiplying by that negative, I get the square root of x. And now, based on what we've been doing, we now know it's shifting in the horizontal direction. This one's kind of tricky, but it's going to shift in the horizontal direction 2, because normally it would start at 0. So what's going to make all of this go to 0? It would shift horizontally 2. So it's going to go right 2, and it's going to go down 3. Right? And then what's interesting is, because the x's are being negated, instead of opening in the positive x direction, it's going to reflect and open in the negative x direction. Of course, you can take a table of values. You can always take a table of values, you guys, always. I already know square root of 0 is 0, square root of 1 is 1, 4 is 2, 9 is 3. We have no negatives, so here's our original starting point. If you feel more comfortable, you can absolutely put in values if you would like. But I now notice it's going to start at 2, negative 3. Of course, if you're more comfortable, just make a table of values. This time if I substitute in 0, square root of 2 is a fraction minus 3. So it gets kind of messy. So I would say instead, I'm going to start at 2, negative 3. Okay. Instead of going to the right one and up 1, I'm going to negate the x and still do the y. So when I negate the x, I still get the y. So I'm going to graph this exact same graph, but instead of going left 1, up 1, right 1, up 1, I'm going to go left 1, up 1. Instead of going right 4, up 2, I'm going to go left 4, up 2. Instead of going right 9, up 3, I'm going to go left 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Up 3. So my graph looks like the square root graph, but it has been reflected about or in the negative x direction. So of course, look at some examples in the book. You can always check some of the other websites, and we'll practice it with a lab.